Hello everyone, my name is Li Yichen. I'm currently doing doctoral research at Huazhong University of Science and Technology in China. The paper I will be presenting today is titled Towards Efficient Replay in Federated Incremental Learning. In detail, my presentation includes the following 5 sections. First, I will specify the background of federated learning and continual learning. Federated learning is a collaborative machine learning framework where a global model is trained by aggregating updates from multiple clients with local data. This approach allows for the preservation of data privacy as the data remains on distributed devices. A prominent example of federated learning is the Fed-average algorithm, where the global model is obtained by averaging the parameters of local models from different clients. Incremental learning, also known as continual learning or lifelong learning, enables models to learn from a continuous stream of data while retaining previously acquired knowledge. This approach is crucial for adapting to new tasks without forgetting what has been learned before. There are 3 primary scenarios in continual learning. In class incremental learning, different tasks introduce new classes, and in domain incremental learning, different classes introduce new domains or distributions, while in task incremental learning, both the classes and domains change across different tasks. Despite the advantages of federated learning and continual learning, several limitations exist. On one hand, current federated learning methods often assume that the data on each client is static. However, in real-world applications, data is typically received incrementally. On the other hand, a significant challenge is the difficulty in retaining previously learned information while learning new data, which is also known as catastrophic forgetting. This issue is exacerbated when the data is not identically and independently distributed across clients. As shown in the left figure below, most existing works focus on either temporal heterogeneity or spatial heterogeneity, respectively, and just a few research address the combination of 2 issues together by federated incremental learning. To address these limitations, in our paper, we focus on federated incremental learning and make an assumption that each client can cache a few samples with the local storage for replay, but lacks enough storage space to retain full sample. Here, we illustrate an example of 3 clients in federated incremental learning theory. With a naive caching strategy, the cache samples by all clients will cause a severe global data heterogeneity. If each client caches samples with a desirable method, the cache samples can contribute to the training of the global model by elevating the global data heterogeneity. Consequently, it is essential to efficiently cache important samples for replay to balance local training needs and global data distribution. In our research, we aim to address the following 2 main questions: how to ensure that samples can balance local training and global data distribution, and how to quantify the importance of samples. To tackle these problems, we propose a reflect framework to enhance federated incremental learning with coordinate each client to cache important samples using limited local storage, allowing for efficient replay during new task training. This framework includes the following key components. The first one is a personalized informative model (PIM). Each client maintains a PIM that integrates local and global model updates. This model helps in calculating sample importance scores, which guide the selection of samples to be cached. The PIM is updated by the equation 3. The second is the sample importance score. Samples are selected for caching based on their importance scores by equation 4, ensuring that both local and global training needs are met effectively. Next, we theoretically prove the convergence of PIM, and the cache samples can balance both the global and local information. Our experiments evaluate the performance of the reflect framework across various datasets and baselines. We use a variety of datasets for our experiments, including CVPR10, CVPR100, and Tiny ImageNet for class incremental learning, and Teacher 10, Office 31, and DomainNet for domain incremental learning. We compare our framework against traditional FL methods like Fed-average and Fed-prox, custom methods such as fix, DAN plus FL, and shared, and existing FIL methods like FCIL and FedCIL. We assess the performance of our refed framework in terms of test accuracy and communication efficiency. Our results demonstrate that refed significantly outperforms all state-of-the-art methods, achieving up to 19.73% improvement in final accuracy. Furthermore, refed requires the least communication rounds to achieve the reported test accuracy on all datasets with its caching method. Thus, the local model is easier to converge. Then, we conduct experiments with different levels of data heterogeneity. As shown in this figure, all methods achieve an improvement in test accuracy with a decline in data heterogeneity, and refed consistently achieves a leading improvement in performance with different levels of data heterogeneity. Then, we conduct more research on the setting of hyperparameter lambda. In our framework, we modify the lambda value to adjust the global and local information proportion in PIN. Experimental results show that the value of the lambda should be chosen accordingly under different data heterogeneity. Nevertheless, results exhibit the same trend. As the degree of data heterogeneity increases, our refed framework performs better while lambda decreases as the PIN contains more global information. Empirically, striking a balance between global and local information is the key to addressing the data heterogeneity in FIL. In conclusion, the refed framework addresses the challenges of the catastrophic forgetting and data heterogeneity in federated continual learning. The key advantages of refed include optimization. It allows for flexible use of various aggregating methods, maintaining convergence benefits. Privacy. It ensures data privacy by not transmitting extra information over the networks. Resources. It enables efficient local training without additional computational or storage overhead. Our extensive experience across various settings and baselines validates the effectiveness of refed, making it a robust solution for federated incremental learning. Thank you for your attention. If you have any questions or need further information, please feel free to reach out to us.